different. I thought I will focus on one single part of uh, the sensing technology rather than talk about broad. Uh, this is we are going to look at the light matter interaction and look at the how we can use that like a molecular calorimetry for chemical sensing. Next slide, please. Okay. So outline, I will talk about the heat energy, micromechanical sensors. Then talk about the Seebeck effect and Seebeck probe for calorimetry and the photothermal effects of liquid sensing and summarize my talk here. The next slide. So MEMS and NEMS are micro electromechanical system or nano electromechanical systems are well known. It's there's lots of literature already out there, lots of products. We used to make micro and nano fabricated structures, like a cantilevers. That's what we started out with, cantilevers as well as bridges and so on. The one of the interesting things about the say cantilever, you can use it as a extremely sensitive mass measurement tool because you can adjust the frequency. The higher the frequency, higher the mass resolution. So people have shown the single molecule detection and so on, but it need a lots of instrumentation to show that. So that cannot be practical sensor, but it can have application in fundamental science. And it also has a very high resolution because you can have a very high Q factor associated with your resonance. You know, in addition, cantilevers, since they are displacement sensors, that's why they are used in atomic force microscope. You can also measure extremely small forces from, for example, adsorption of molecules on the surface. And we can have a wide dynamic range in sensing. Another interesting thing about these MEMS and NEMS is that you can have a extremely small mass. So that means small thermal capacitance. So if you, for example, a small thermal mass material or thermal capacitance sensor absorb a photon, that entire photon assume it's absorbed, then that will become a thermal energy at the end, and it can have a very high temperature because the thermal mass is extremely small, so temperature has to high to balance the energy. You can also look at the material properties, the electrical, thermal, optical, all different properties. So MEMS and NEMS basically opens up all different possibilities for sensing, and that's what I am focused on. And in addition, one thing I forgot to mention is that you can, for example, a cantilever can have multiple the responses to a to a entity. For example, the cantilever amplitude can change, vibration amplitude. It can, the frequency can shift, its bending can change, and the Q factor change, and also the phase. So you can have multiple things, parameters to monitor the response of the cantilever, for example. And next slide. So this is a simple microfabricated cantilever is showing a little cartoon. They're looking like a diving board, and generally we make this into arrays, and to for, to make it a chemical sensor, we always add or functionalize one of the surfaces with some selective agent like a surface, self-assembled monolayers or thin polymer layers or metal or semiconductor or any of those the surface with a different chemical energy for absorption. And the adsorbed mass is a delta M is given as 2 times delta F was a shift in frequency by the original frequency times the mass of the entire system. The bending Z, the free end of the cantilever, is proportional to the change in surface energy, which is sigma or surface stress, divided by Young's modulus, multiplied by length divided by thickness whole square. And if you make the cantilever as a bimaterial cantilever, then the change in temperature we can measure in terms of change in bending. So delta T is proportional to delta Z divided by E1 alpha 1 minus E2 alpha 2. E1 and E2 are the Young's modulus of the bimaterial components. Alpha 1 and alpha 2 are the coefficient of the thermal expansions. And this bimaterial cantilever, an excellent thermal sensor. It can detect changes in temperature as small as the 10 millikelvin. So it's very high temperature resolution without any cooling required. Room temperature. So excellent and very simple thermometer. Next slide. So we have made it into arrays of this thing, and the beauty of the cantilever arrangement or MEMS arrangement is that you can make them into arrays of hundreds of these things. And as I said earlier, cantilevers are physical sensors. They measure mass or the bending, which is surface energy, or temperature. These are the things that it can easily measure. But how do we make this into a chemical sensor? Like I mentioned a little earlier, we put a self-assembled monolayer or some kind of a receptor or chemical interface. This is a technique or an approach borrowed from biology. Biology, antibody antigen come and interact with each other. So antibody will be immobilized on the surface of the sensor. Antigen comes in, it binds. It can change the mass, or it can change the surface stress, or one of the other physical properties. So if you have an array of cantilevers, you can have each of these cantilevers modified with a different type of chemical interfaces or receptors. You can detect almost a array of chemical present in a or biological analytes present in a medium. So at the bottom, what you are seeing is a little device we made a long time ago, actually. And it is the size of a pill. It's a pill size of a quarter, US quarter. And it works with the 2 hearing aid batteries and the titanium fret. Titanium fret that to allow the vapor to go in to this pill, and the cantilever changes its bending, and there's a wireless telemetry included in it, so it can transmit the data outside. The reason we didn't continue this too much is that originally it was intended as a implantable sensor, so that can be implanted someplace in a body, for example. Unfortunately, the batteries have limited lifetime, so you cannot implant it for too long. So battery became a big problem. So we basically discontinued this part uh, because we didn't know how to address the battery challenge. But later we came up with a single wire transmission, which I wouldn't talk about it here. Next slide. So the Achilles heel of this selective coating or receptors is that most of these receptors work by molecule detecting another molecule concept. However, there can only be very few interactions that we can use to design this interface, because we want this sensor to work reversibly. So that means when the analyte or the target analyte is taken away from the sensor area, sensor should come back to normal. It should regenerate itself. That means it should be a physisorption. Physisorption is basically van der Waals interaction or hydrogen bonding, because thermal energy KT, KB is the Boltzmann constant. For room temperature, KT energy will be around 4.14 times 10 to the power minus 21 joules. So that is a hydrogen bonding. So if you increase the interaction energy into covalent energy or something, then it will be very hard for this to reverse. So you have only choice between irreversibility and high sense selectivity, or reversibility and not that selective. So chemical sensing is basically molecular interaction, and it is controlled by the chemistry of the interaction. And like in real estate business, where location is the key, and in sensing is the selectivity. If we don't have selectivity, we have no sensors. Next slide. So this is where the thermal energy comes in. As you know that heat is nothing but the energy in motion. All irreversible process finally end up as heat. Molecular interaction generate heat, and optical interaction also, especially in the mid-infrared region, can also generate heat. So we can, for example, excite a molecule resonantly using infrared light. So it is excited into higher vibrational state. And there are two ways it can come: radiative relaxation by giving out a photon, or it can also give out the non-radiative way. That means the energy levels are so close together, they will basically generate heat rather than radiation. And vibrational energy of these molecules are around 10 to the power 14 hertz. So it's very fast, this process are happening. And the molecules can vibrate in ways, so itself is a complex area. And for example, in a 1 second time, 1 second sampling time, a single molecule can be excited millions of times if we have enough photons to hit it with. So it can get excited, 10 to the power minus 14 second, and then come down, and then it get excited again. So you don't need so many molecules, you know. And so, so the heat basically adds up. Like I mentioned earlier, if the thermal mass or thermal capacitance is extremely small, the temperature of the device is going to increase. So why is it important? Because if you are looking for a high, the ultra trace detection, high sensitivity, so like a parts per billion or parts per trillion range, generally what people do is that they use pre-concentrators, try to collect more and more molecules for in a few minutes or so, and then release them at the same time by heating or so, and then the sensor detect a little higher concentration than before. Next slide. So let's look at the heat energy. So for example, a bacterium produces 10 to the power minus 12 watts, a picowatt, and if you look at the human being around 1,000 watt or something like that. So you can see the scale of things. Heat is everywhere. And interesting thing, for example, is that bacterium is not that efficient. It is a 1,000 watt per kilogram. I mean, that's what they use. For human, is a 1 watt per kilogram. So humans are 1,000 times more efficient than bacterium. Very interesting. We will look into this in a later part of this talk. Next slide. So let's look at the Seebeck effect. Seebeck effect is basically a thermocouple, basically. So basically, you take a piece of wire or a metal or a semiconductor, you heat only one side. So there is a gradient. So as you know that lattice atoms are basically fixed in space, but the outer electrons are movable from the free electron theory. So when you heat one side, these electrons are going to move away from hot side to cold side. That's the way we can imagine at this time. And it generate a electromotive force. So one side will be positive and another side will be negative. The voltage difference, dV, is equal to minus some Seebeck coefficient S times the delta T. So S is the Seebeck coefficient, and it is extremely small. It is in the range of microvolt per K, or even maybe sometimes, sub millivolt, 100 milli, not 100 milli, much lower. So that's why most of the time these thermocouples are arranged in groups, so you can actually increase it. No, so generally you need to measure the potential difference. You need another probe, actually. Or so in a thermocouple, it is accomplished by having two different materials with the two different Seebeck coefficient, say A and B, and they are connected together at one end, and it's free on the other side. And wherever you connect it, that become the hot junction. So you heat that part, and you can measure the potential difference between the free ends A and B. So the delta V is given by this equation, but this is a very simple equation. You don't need a integration actually, because it depends only on the hot and cold temperature. It doesn't depend on the path of the temperature change. So the path can be any different change in temperature. It doesn't matter. The only thing is matter the hot end and cold end. So you can basically write it as the Seebeck coefficient difference between the two material times delta T. Next slide. So this is a Seebeck probe, which is a cantilever, and you can see that it is actually it can also be used for atomic force microscope, and the pyramidal end, and that's where the two material and two elements are actually buried in the cantilever structure. Cantilever is the freestanding, and the junction is at the free end, and the diameter of that free end of that cone is around 50 nanometers. So 25 nanometer in radius. So this is where the two metals are coming in contact, and the thermal resolution of this material, the arrangement is around 40 millikelvin. So compared to a cantilever, for example, 100 micron cantilever, the coated with say aluminum or something, you can get 10 millikelvin pretty easily. And here is you can see that is 4 times, at least 4 times higher. But the beauty here is that the amount, the area is very small. On a cantilever, area can be 10 to the power minus 8 meters square. And here, so thousands of times, million times smaller area compared to that of a cantilever. So if you want to study, a few molecules, or then this is the best way to do it. And the inset that you see little dots, those are the nanoparticles actually. So you can use this 25 nanometer area to do all kinds of self-assembly and so on. This particular image of the nanoparticle is not done on the not at the tip. It is done on another surface. We are trying to get it, do it on the tip at this time. Next slide. So now assume these molecules are absorbed on the surface, and you are hitting it with a infrared light. So in this picture towards the bottom, you see a scale, shows the wavelength, and 3 micron to 14 microns. And you can see that different molecular groups have very unique vibrational frequency, that is shown here. So like for example, in the 3 to 5 micron range, basically used for environmental monitoring. 7 to 10 micron area, 7 micron to 10 micron wavelength range, the can be unique for chemical agents and explosives and things like that. And towards the higher side is used for biomedical breath analysis and so on. Uh, these are done in the FTIR and Fourier transform infrared spectroscopy and things like that. And that's why the infrared spectroscopy, especially in the mid-infrared, is known as the molecular fingerprint regime, because this signature unique. So you can have mixtures of the chemicals on it, and but you can still identify them by looking at what peaks are available. And if you have all kinds of mixtures, then you may be able to use machine learning to figure out the target molecule is present there or not. So the diagram on the right side shows, it's a cartoon again, molecular vibrations, and when the molecular vibrations are excited in the higher states, they have you can have the non-radiative decay. That means the energy levels are so packed together, so they can just look like a continuous. So they basically lose energy as phonons, not as photons. Next slide. So we took one of these Seebeck probes, and then we have, like I said, it's only 25 nanometer in radius. This is a PDMS on the surface, very small amount. And we are going to excite it with heat it with by shining 1400 centimeter inverse. Instead of micron is a 1 over uh, lambda right now. So to 1400 to 1150 wave number centimeter inverse. And you can see that the different peaks that you see, this is come from the whatever molecules are absorbed at the tip of the cantilever, that Seebeck probe. So you can easily identify this peak as the PDMS peak. Next slide. So this is the arrangement. Again, we right now we are using a quantum cascade laser, but you can also use any tunable IR. We also have a glow bar with a filter wheel. We use that one too, so it works fine. And then you chop this light, infrared light, and then expose the cantilever with material on it to this light, and then look at there's a preamplifier because we have very small voltage induced, and then use a lock-in amplifier to reduce further noise by chopping it. Use a chopper of certain rate. So what we have shown is that we can chemically detect, or we can get the chemical signature of 10 to the power minus 18 gram of material adsorbed on the surface. And we demonstrated this with TNT, trinitrotoluene, DMMP, which is a chemical simulant, chemagen simulant, SU8, and PFAS, perfluoroalkyl compounds. And since this Seebeck probe is also a cantilever, we can measure the mass on using that idea too. But remember that Seebeck, the signal comes only from the tip of the cantilever. So the entire mass doesn't matter. So when you pick up the material only at the tip, then measuring 10 to the power minus 18 gram using resonance frequency is extremely hard. It's very difficult to do it at this time using this type of cantilevers because they don't have the high frequency. So generally we don't measure frequency. I mean, you use it, but we don't basically worry too much about it. But you estimate the amount of material at the tip by comparison, by calibration, basically. So how much is absorbed on a cantilever or a quartz crystal microbalance, and then we can calculate how much area, and then we have 25 nanometer radius, so that must be the amount absorbed on the surface. And this around in the ballpark, it must be right, and that's where we get 10 to the power minus 18 gram. The next slide. So we also have modeled this thing. So we can model this using, this arrangement using a thermal capacitance of the material, and at the axis of this pyramid, that's where the thermocouple reside, nanoscale thermocouple, and our calculations pretty much agree with our measurement. Next slide. So these are some of the data, the infrared data collected using the Seebeck probe and TNT, and that's a top one. And then the bottom one, the red one, the FTIR taken at the same time with a different sample for TNT, so we can have a comparison. And the PDMS, green, and the red is again the FTIR. Same goes with the DMMP and PMMA. And you can identify different peaks, which vibrational mode it corresponds to. There are very interesting things happening here, which we haven't studied in detail. For example, the width of the peaks are very different compared to that of FTIR. So that has to do with this thermal capacitance and things like that. So we are still investigating that part, but for analysis, these peaks are perfectly fine. We will be able to identify this peak and identify the molecules. So next slide. So this appeared in the nano letters recently, and again showing the different way of doing it. Either you can evaporate the whole this thermal probe, Seebeck probe, to vapors, so molecules are absorbed everywhere, and then you get the signal. out of the sea. Or you can, since this looks like a atomic force microscope cantilever, you can load this on a atomic force microscope, and then assume there's a TNT adsorber on a surface. You can go there and then pick up just enough material at the tip. So AFM can also be used to pick up material, at the end of the tip, right? So that's what is shown here. And we show that, the signal look exactly same. So whether the molecules are adsorbed all over the surface or at the tip, the Seebeck effect comes only from the junction. Other part, it doesn't really contribute. Next slide. So now we are moving into the cantilever. So this is basically showing a regular cantilever. Uh, so cantilever has uh, we shown that the Seebeck effect can be used to detect 10 to the power minus 18 gram, and much better. But the cantilever can be used for a higher amount of material, but the signal can be very, for example, photothermal signal here. Like instead of the Seebeck effect, we are using a bimaterial cantilever. So the whole cantilever has two metals. The silicon and another metal, like aluminum or gold, and the molecules are absorbed on all over the surface, and then you can hit it with light, the from different wave numbers, and then get the peaks of different molecules absorbed on the surface. And that's what is shown here. This is PFOA, is another PFAS, and the bottom part shows the resonance frequency change. And as you know that this resonance frequency is very small, so it is a long cantilever. It's almost 500 micron long cantilever. So the area is large. So lots of materials are absorbed on the surface. As you can see that the mass resolution is not very high here, but you can see the peaks of different the PFAS, the vibrational amplitudes are shown clearly, and it matches pretty well with the FTIR data. Next slide. So this approach, the cantilever can be used in two different ways. One way to do is was a integral approach, and in the integral approach, where you chop the light at a very low frequency. So it's like 100 hertz or 20 hertz or so. So within that time, the cantilever keep receiving the photons, and whatever molecules are absorbed, they get excited and de-excited. So heat adds up. So cantilever keep bending because of the bimetallic effect. So we can also do it in a dynamic mode. So you can actually vibrate the cantilever at its resonance frequency. So you can have each of the vibration vibration is maybe 10 to the power minus 3 seconds to minus 6 seconds, 10 to the power minus 6 seconds. Basically, it's 1 over f. So, and then you look at the amplitude. So you're changing the different wavelengths, and exposing the cantilever and only looking at the amplitude. So this approach give you a very fast detection. So, and it also compatible with the mass measurement at the same time. Next slide. So what about the liquid? So people ask this question, we want to detect liquids because liquids are more interesting for all kinds of applications. So this is a cantilever with a you can see the cantilever at the bottom, and there's a microfluidic channel. Next slide. So yeah, one more. Okay, so this you can see the this SEM pictures shows how this channel looks like. It's like a U-shaped channel built on the top of the cantilever, and it's around 10 micron in width and then 3 micron in height. And actually, we borrowed this idea from Scott Menalis, who used this type of arrangement for mass measurement. So we are trying to use it for all different approaches. Next slide. So here shows what else you can do with it. So you have this cantilever with a microfluidic channel on the top of it. Now you can resonate this device and look at the change in frequency with and without liquid. You can get the density of the liquid since the volume is fixed. You can also look at the Q factor, I mean, the full width at half maximum of the resonance amplitude, and that will give you the viscosity of the material. And then you can shine either UV, visible, IR to get the spectrum, or you can look at the thermal properties by hitting it with a light source, I mean, thermal source, and so very lots of interesting uh, ideas can be developed from here, because the volume of this channel on the top of the cantilever is only 50 picoliters, so it's extremely small, and the volume is fixed, and you can now change the temperature, you can change the pressure, and you can do all kinds of thermodynamic calculations from or the measurement from here too. The next slide. And so this is an example one, a molecular recognition of 50 picoliters of, say, fumarate, and the B shows the glucose. They are in physiologically relevant concentrations. And then basically you are looking at as you shine different wavelength, this get it changes the thermal properties because the molecules are absorbing and the cantilever bend. And so you record the cantilever bending as a function of wavelength, and you get the spectrum of fumarate and the glucose. The next slide. So next example is about the bacteria. So you have a 50 picoliter volume of the channel. So we used a peptide modified the inside of this channel with peptide and send bacteria, and the bacteria trapped inside the so there's a question, are these peaks coming from the cantilever? Yes, the cantilever bending, basically, right? So here we are using the peptide is actually, coated inside the channel with the peptide, and you send the bacteria get trapped. So it's basically enriching the number of bacteria. The more you pass the liquid, more and more bacteria will get stuck inside. And now you can look at their mass, you can look at their change in energy uh, by looking at the bending, adsorption energy. You can also shine different wavelengths, and that's the bottom part shows a C on the left side, right side. Oh, there's a question came up saying that do we have to connect the cantilever to a software? So basically, yes, you have to. I didn't discuss that part. I can discuss that part a little later. And so you're looking at the bottom on the right side shows the infrared spectrum of this at the various stages. So you can see that. Look at the difference and see what is the signature of the bacteria. Next slide. So now the interesting thing that you can do with this arrangement is that you can do lots of say interesting chemistry or biology. So what is shown in the top is that you have bacteria trapped inside with the PBS buffer solution, and you can see the red curve shows that the noise in the cantilever is vibrating. It's like so that is in terms of nanometers. So you can see some kind of noise because bacteria is active. Bacteria are active in the thing, so they are. Now you send some sugar solution, that is the B, and you can see the red curve basically increase the noise. So the bacteria consume sugar solution, and then they are generating heat and they're happy. That's the noise. And now you send some ampicillin, which is a drug that can kill the bacteria, and 30 minutes after you send the bacteria, you can see that the noise actually decreased a lot. That means the bacteria may be dead. Now you send the sugar solution again, but the bacteria doesn't come back to life again. So the bacteria dead, right? So you can look at the drug interaction with the bacteria this way. A very small amount of 50 picoliters solution. So you don't need very much drug, a very small amount of drug. So if you're looking at a very expensive drug you're developing and you want to test it out extremely small amount, this may be a good idea. And the bottom part, which is shown in green, are done with a different drug, kinomycin. The top one is ampicillin, and you can see that again when you give the PBS buffer solution, the bacteria have some similar noise as earlier. But when you give the sugar solution in the B, in the figure B, and you can see that noise increases. And then you send the kinomycin, and then unfortunately, the kinomycin doesn't do anything to this bacteria. So it doesn't change anything about it. So when you send it to the sugar solution again, they come back to life. So next slide. So you can also look at this live versus dead bacteria. You can look at the fluorescence and IR signature from this. So we have all published this many years ago. So this is an interesting opportunity to look at the interaction between different drugs and the biological material, uh, or different type of chemical things happening like catalysis and all kinds of interesting things. So this opens up a totally new area. So again, like I said, you can look at the changes in the mass, changes in the energetic, the bending of the cantilever, and also infrared spectrum, which is basically thermal signatures. Next slide. So the third example, again, this hollow channel cantilever, is to use it for, say, DNA unraveling. So DNA is basically a double-stranded, two single-stranded bond together with A goes with T, G with C, and so on. But when you heat them at certain temperature, they basically unravels into become two separate DNA strands, single-stranded DNA. So double strand becomes a sigmoid curve, and because it's a statistical effect. But how it is done is still controversial, whether the DNA is going to open up like a zipper from one end to the other end, or open both ends, or will it form some kind of bubble in the middle, and then bubble grows. So we have designed some DNA and then filled this channel with that DNA solution. Next slide. So basically this shows that the first one is showing the optical density measurement. That's what people do all the time. Biologists prefer that one. Uh, and they say it's done with a large uh, amount of material. and you take a sigmoid curve. If you take a differential, you'll get your peak, and that is the what you call the melting temperature. And we do the same thing inside the channel. There are around 10 to the power 7 molecules. It's still large number of molecules, but we can get a smaller and smaller number. But what we see is that like in the bottom curve, there are different, there are, it's not a smooth sigmoid curve as you expect. There are some variations. Next slide. So this is the response as a function of temperature. You changed for a couple of different DNA strands, different sequences, and you can see that there are the peaks are no more the same as that you see in a sigmoid where everything is washed out, large quantities. So here you can see the more fine details, and then the statistical mechanics get a little more complex. I'm going to skip that part because that may be a little controversial how it, it's still controversial how it is opening up and what we are seeing, and our interpretation. Next slide. So I will summarize here, the calorimetry, which is the measuring the heat using low thermal capacitance devices can provide a very high specificity and sensitivity when you couple it with the optics. Chemical sense that brings a very high chemical selectivity. And a Seebeck effect is extremely interesting effect for looking at extremely small amount of material, and the hollow channel cantilevers can do all kinds of exciting opportunities for investigating the material in the liquid phase. One next slide. So this is all the acknowledgement I have, and so work of lots of people, and I realized that I didn't include any of this electronic part of the question was there, whether how do we do the electronics. I can explain it in 1 second. And the image that you saw seeing is Buffalo in last December. We had a big snowstorm, and you can see that all houses are buried in lots of snow. So we are talking about the heat. Right now outside is also very cold. So uh, we're talking about the electronic part. Some of these cantilevers are made piezo-resistive cantilevers. So that means when the cantilever bends, the resistance changes, and that can be used. You can use a Wheatstone bridge, basically, to measure the bending with respect to a standard cantilever. So if the cantilever is bending, and its resistance will change because of the piezo-resistive effect. So it's not very complicated electronics, but you have to be careful to make sure that the noise and things like that be taken care of. You know, I will stop here, and I will be happy to answer anything that you may have.